Good morning, everyone. I'll let the people roll in. We have already 4 people. 8.
One of my co-authors is supposed to be there, so that'll be good.
You can see who's coming in by pressing on participants. Yeah, good morning, everybody, and welcome again, or good afternoon, good evening, wherever you are in the world. This is EMinar Wednesday, and it's coming from the coldest capital in the world, -27 right now outside. I'm not going outside today, so it's very appropriate. We have somebody from the southern hemisphere where it's +27 or more. Yeah, it gives me great pleasure to have Sue Webb give this week's EMinar, and we'll talk a little bit more about Sue in a minute. But first of all, some of you may not have been to an EMinar before. You can go on to the MTNet EMinar page. You'll see it linked here, and there you'll find links to upcoming EMinars that you can register for, and past EMinars that you see the videos of, and get the PowerPoint presentations. So we have a couple of, these are mostly EM-based EMinars, hence the name. But we have a couple that's much broader interest. Simon Jarrett of Las Vegas will talk about mining for net zero on the 23rd of March. And Mark Zobak will talk about CO2 sequestration on 27th of April. And so those really exciting, broader ranging talks. So you're on a Zoom webinar, not a meeting, so you can send a message to the panelists. You can adjust your audio settings where your sound comes from. You can send a question in Q&A, please. Don't send it in chat. And you can raise your hand at the end if you want to come online and talk, and we'll authorize your voice. So next week, quick advertisement for next week, it's Kurt Strack. He was due to talk later in season 2, but he's been brought forward because we had a late cancellation. And Kurt will talk to us about using high power control source EM during the energy transition. But today we have Sue Webb, and I've known Sue for quite a while, 20 years. And Sue's going to talk about something that's related in a way to electromagnetic induction, of course, lightning strokes that we use for our AMT signals. And Sue's talk is Flashes of Brilliance, linking magnetic evidence for lightning strikes with weathering the regional lightning networks. And some of you will know Sue very well. For those not that familiar, Sue came through various universities, including Memorial University in Newfoundland, and then went to University of Witwatersrand and joined WITS in '94, and she's now an associate professor, and worked on a number of international projects, particularly CAPVAL project and the SAMTEX project, Africa Array, and working as a co-PI in the Bushveld complex drilling program. So I'll get out of here, Sue, and invite you to share your screen and take it away.
Okay, here we go. I'm going to do that and share. And there we go. I hope you can see my my screen there and hear me okay. We tested this earlier.
All good. It's all good.
Okay, fantastic. So I'd like to introduce my co-authors. I'm working with a diverse group of people. Jasper Knight and Stefan Grab are from our geography department. They're more on the geomorphology side. And Hugh Hunt and Karina Schumann are from the electrical engineering side of things. So we're combining very different fields. And myself and Stephanie Enslin are from the geophysics side. So it is quite a collaboration. Let me get my laser pointer is on and I can do page down. There we go. So magnetotellurics uses lightning and the effect of lightning. Certainly at frequencies higher than 1 hertz, lightning is the main source of the magnetotelluric signal. And so this animation is one that I pulled off the web, and it's showing a year's worth of lightning strike data that's global and shows how it varies from the northern and southern hemisphere. And it's mainly the equatorial region where the lightning is most intense. I'd like to show a video from Karina Schumann, who's been doing some very interesting work in Johannesburg, recording lightning strikes at 20,000 frames per second. This is just incredible footage here, if I can get it to show. Now, why doesn't it? Oh no, we just tested this. I guess I can't do it with the laser pointer on.
No, I think you have to turn the pointer off. Yeah.
Yep. Okay, well, that's kind of odd. Okay, so here we go. 20,000 frames a second. That's what a lightning flash looks like. And we'll look at some of the details of that as we continue on. Okay, turn that back on and go on for the next one. There's a long history of lightning studies at Wits University. And in fact, the Bernard Price Institute for Geophysical Research, which was founded in about 1937, was actually, Basil Schonlen was appointed as the founding director with the specific task of researching lightning and electric fields. So it's interesting that we're working together again with the electrical engineers on this project. And so this is quite exciting. So why do we study lightning? Well, there's a fairly large number of fatalities in South Africa due to lightning. Fieldwork safety, we have to emphasize that to our geoscientists, that lightning is actually quite dangerous in the field. There's also infrastructure damage. It's a source of the MT signal, and we'd like to know more about that. And I'd also like to point out another aspect that it isn't really lightning, but during the St. Patrick's Day storm of March in 2015, there was the geomagnetic network was utilized to model the induced electric field. And it looks like even in these latitudes we have in South Africa, that anomalous currents could be induced that damage the power distribution infrastructure. So all of these electrical and electromagnetic effects are affecting our lives here in South Africa. So it's not just lightning, but also the solar winds and these geomagnetic storms that happen. So what does the sensor locations look like? We've got a South African lightning detection network, which is run by the company Vaisala. And there's a fairly good distribution of stations all over the country. So you can see here where we're certainly in 2013, there were 24 stations that were out. And this is what they look like. This is an installation on a rooftop. And it's interesting to compare the lightning sensors with the magnetotelluric sensors. Probably everyone on the webinar is familiar with the magnetotelluric sensors, which have an electrical, two components of the electrical field are being recorded, and possibly three components. Most often, sometimes the vertical component isn't recorded, but two magnetometers, X and Y. And it's very similar to the lightning sensors, which have two right angle magnetic field coils. But here they're collecting the vertical electric field instead of the horizontal. So that's a major difference. But it seems like there ought to be a way to cooperate with some of these data. So the lightning sensors are very similar to the MT sensors in principle, although they're recording different frequencies perhaps. And a question might be, could we somehow use magnetotelluric sensors to supplement lightning sensors, or can we co-locate magnetotelluric and lightning sensors and use the vertical electric field somehow? And I'd like to point out that there are 10 long period magnetotelluric sensors in South Africa as part of the South African National Space Network for electric current studies. So these have been sitting out in South Africa for almost 10 years, collecting data for a long, long period. So these are the MT stations. Sorry, let me share that. So the upside down triangles in orange are actually long period magnetotelluric stations. What does the electric field sensors look like? This is a photo from Hugh Hunt that shows one of the sensors on the roof of one of the buildings at Witts University. So they're collecting at very high frequencies and they're recording a tremendous amount of data, 1 file per second, that's GPS timestamped to high detail. So how are the data processed? Well, they're triangulated, very similar to how we record earthquakes. And in fact, this could have come out of an earthquake textbook. And so it's a very similar type triangulation. You're looking at the travel time to the sensor and drawing a circle around it. So you need at least 3 sensors to locate the actual lightning flash, and you compute where the stroke location is. So that's very similar to what we do in seismology. And in fact, the density of the lightning flashes is shown here this is from 2008, but it could be similar over the years. And you can see it's quite high density, especially along the Drakensberg, along this very large change in elevation. What do the data actually look like? Well, this is just a screenshot of some of the data that comes in, and you can see the time is down to nanoseconds. You've got your latitude and longitude. But note here, we've got an ellipse angle and a semi-major and a semi-minor axis. And so what the data are presented as is confidence ellipses. And this is how the data are given to us. We don't actually have access to the most raw data to do our own locations. This is what we're provided with. So we have to work with these data. And here's an example of what the location would look like with the confidence ellipse around it. And you can see this big tall tower here. And that's really where all of these would have struck. These would have all struck this tower. And in fact, if I remember right, this is actually one flash, which has several strokes to it. So these all would have been tied to this tower in location, but they have slightly different locations depending on how the algorithm works. And unfortunately, we don't have access to that algorithm. So we have to work with the data we have. And we can play with the data and do different kinds of maps and the way we count the strokes, changing the resolution and all of that. And that's some of the work we're looking at, is to try to understand how best to use these statistics in our study on the lightning strikes in Lesotho. So what is detected? So here's another one of Karina's wonderful videos. You can see we have what we would see as a single flash. When we look at it at this super, super high detail, we saw that one strike come down, we see another stroke and another stroke. We'll often get several strokes with a single flash. And so these little peaks all have to be accounted for and attributed to a single location. And I think we'll have one more big stroke at the end. I think it's coming. Where is it? Where is it? Okay, we'll move on. I know there's a big one right at the end. There we go. Okay, and you can see they all come along on the same exact path. And so let's now look at what is the evidence on the ground for lightning strike. And we're probably, as geophysicists, mostly familiar with lightning-induced remnant magnetization. Anyone who's tried to do a paleomagnetic study in South Africa has probably given up on any outcrop, because most outcrops have been struck by lightning at some point. So we tend to use road cuts, we use quarries, we use underground, because those have not been affected by lightning strike. And this is an example of a suspected lightning strike in the Vredefort impact structure, so about 100K south of us, south of Johannesburg. And what is the evidence? Well, one of the people that lives near there said there was a big lightning strike. They obviously weren't close to it, but they said it was somewhere over there on the hill. and you go out there and you find a burned tree. So we can see this tree was actually burned, incinerated, and you can see the rock spalling. Now, this has caused quite a bit of controversy because sometimes, you know, in this area, we're not supposed to use rock hammers because it's actually part of the World Heritage Site. And so if you come across a rock that looks like this, you might think a bunch of students have been banging on the rocks, when in fact, it's actually a lightning strike that has blasted off chunks of the weathered rock and exposed some fresh rock underneath. So here's my co-authors, Stefan Grab and Jasper Knight and Roger Gibson, who's an expert on Vredefort. And we're investigating, we're looking at all of this damage that was done at this particular site, where we're pretty convinced that this is a lightning strike. And there's a number of these in the area. And you can see this is close to the topographic high. They're frequently on the kind of edge of the topography, not necessarily, also often on the top, but not very far below the edge. In Vredefort, of course, we're in the granites here, so it's quite smooth rocks. This is right on the edge of where the granites run into the sediments. Okay, and these are just some other views of this incredible spalling that we get. And so the question is, how much of an effect does this have on the actual rocks in terms of the magnetic properties? And that was a study done by Karposen and the other people I know there are Stuart Gilder and Roger Hart, who's a South African colleague. And they looked at a site in Vredefort, now here shown by the star, which is well within the granites. And you can see the area here, they chose a fairly small area to look at. And each one of these X's is 10 meters apart. And they drilled all of these out for a paleomag study, but then they also had 2 deep boreholes into this suspected lightning strike, Vredefort 3 and Vredefort 2, which were 10 meters deep. And so they collected paleomag data all the way down these 2 boreholes and also all over this grid. And I'm just going to look at the borehole information. So you can see here are their inclination and declination data from the boreholes as they demagnetized and looked at them down in depth. And you can see that the lightning overprint affected the rocks down to about 4 meters, has a strong effect down to about a depth of 4 meters. So that's an interesting data point in terms of how deeply rocks are affected by an actual lightning strike. And so this was quite an interesting study. And it's one of the few, I think, that has actually drilled deep enough to really demonstrate how deeply lightning affects things. Now, we don't know what type of lightning strike this was. There are different types of lightning strikes that have very, very different energy that they put into the ground. And that's one of the things we're looking at with the electrical engineers, is to try to understand which lightning strikes are likely to cause the most damage, that have the most energy, and are likely to explode the rocks more and change the remnant magnetization. So these, in this diagram here, we've got the magnetic data that, ground magnetic data that were collected by Karposen's group. And they used a cesium vapor magnetometer with a sensor height of 2.55 meters. And this is the little map they made. We studied the same exact area with our own magnetometer, which is actually basically the same one, Geometrics 859, sensor height of 2 meters. And we did a little bit larger area than they did because I just wanted to see how, you know, cover a little bit more area. And we get almost exactly the same results in terms of amplitude and shape of the signal. I just didn't plot it in exactly the same viewpoint they did, but we go from 17,000 nanoteslas up over 38,000 nanotesla. So it's quite a range, 20,000 nanotesla range. and the susceptibilities don't really change that much. So let's have a look at Lesotho, where Stefan and Jasper Knight have been working on the geomorphology of the lightning strikes. And so here is the country of Lesotho, and you can see from a geological point of view, it's in it's basically the Karoo supergroup and the Drakensberg lavas. And one of the aspects we've kind of looked into is people tend to think, well, shouldn't lightning have some kind of an attraction to different lithologies of rock? Well, fortunately up here, there's only one lithology, so we can discount that. But all of the studies that have been done demonstrate that topography has a much, much greater effect. And in fact, it's almost impossible to see any effect of lithology on lightning location. So there are a few questionable studies out there trying to use lightning to map out fault zones and use it to find oil. So just have a very careful read of that kind of literature. It has been published, but I would be quite skeptical myself. So have a, use your own evaluation of that, but it is certainly other studies have shown that there's absolutely no correlation with lithology, but we don't have any problem here because all we've got is basalts. So we've got the Drakensberg here, we've got our study area is here, and it's very, very close to the tallest peak in Lesotho. And one of the reasons for this is that we want to be away from any way that rocks could fall on our site. So we want to be at the highest possible elevation, so nothing can be said to be falling on us. If there's rock rubble, it had to come right from that site. This is just an incredible image of the Sani Pass, which you have to drive up. South Africa border post is down here, and the Lesotho border post is way up here. I'm not quite sure who this land belongs to, but it's one of the most spectacular drives on the planet. And but I think it's been paved now, unfortunately. And so what Jasper and Stefan were able to show is that lightning is actually an important geomorphic agent on mountain summits. And the idea is that lightning actually breaks the rocks as much or more even than, say, freeze-thaw damage to the rocks. So they were able to demonstrate from their geomorphology evidence that this is the case. And so here's an amazing capture of a lightning bolt striking near Lesotho by Brian Mallinson. And you can see in this just explosion of color here, how much energy is imparted to the rocks. So this is a view of our study area, and we're about halfway there from where we parked the cars, and we had to walk all the way along here and then up around here and then all the way through here and then up, and we entered onto the site through this little gap. And so this peak is one of the areas we studied, and then we also studied this kind of ledge. So we were on top of this ledge, and that's where we collected. Stefan and Jasper have done a quite extensive study of identifying what they think are actual lightning strikes from the fracture of the rock. And then we came along with the magnetic, the total field magnetics to demonstrate where the remnant magnetization has been changed, because of course then the total field will change. If you have a large remnant component contributing to the magnetic field, in addition to the induced component, that will change your total field. So we'll look at those data. So this is now using Google Earth to look down at the site from the top. This is our little tiny peak up here. And this is this edge of one particular basalt flow that is more resistant and is creating this edge, which is struck by lightning. Okay, and here, just to bring you into the picture again, this is the very, very tippy peak, and this is our little ledge. And these are the strike sites. This is from one of the papers by Knight and Grab where they've identified and discussed a number of sites in detail. And we're just going to look at these sites here. We're not going to look at this other peak over here. And they've identified other ones that they didn't really have time to discuss in detail. And so what do they look like? Well, this is an example of one of the identified lightning strike sites. And you can see the rock is fractured and the rocks are actually thrown quite far in some cases. And in fact, sometimes you can find a piece that's 1 or 2 meters away. And the question is, could freeze thaw actually do that? Does that make any sense? And probably not. The more time you spend up there, the more you become convinced that this is actually exploding and fracturing fresh rock in cases. Here's another case of where the rock, you can almost see how to puzzle it back together. Not entirely convincing, because we do see some weathered surfaces here, which would suggest that even the lightning is taking advantage of previously fractures and cracks that might have a little bit of water in them and could be exploding the rock. And here's another one where that's very, very obvious, where the weathered surface is showing up quite nicely here, but this is a little bit fresher rock. But this one is quite convincing. This is plumose texture, which is associated with very freshly, basically fractured rock or exploded rock. And this is right up on the peak. And this was one of the proposed sites of a lightning strike. And we can compare that plumose kind of pattern we see here with just down below on the main road. They were actually expanding the road and using dynamite to fracture the same lithology. So it's the same kind of rock, just another basalt layer. And you can see that exact same pattern within the rock. So this is a blasted road cut very near the field site. When there's a lot of water around, the basalt actually weathers in this way. So it has a very, very different weathering pattern when there's extreme amounts of water. So we know that in the area right up at the top, there's not huge amounts of water. This is further down where there's a whole fracture system and there's a lot of water flowing through this area. And we get this kind of onion skin weathering of the basalt. So let's just look at some early study we did with a honor student. This is Christy O'Brien, and she's shown here with our magnetometer, our walk mag. And what we've done is we've identified a particular feature. It's one of the sites that Stefan and Jasper identified. And we've collected magnetic data all around it at 1 meter spacing in terms of both X and Y. Whoops. Sorry, where did we go? Okay, so here are the actual results from her little studies, and we've got 4 different strike localities. And what we found is that the fractures in the rocks don't exactly correlate with the magnetic signatures. So it's actually remagnetizing the rocks, not in exactly the same place that it's fracturing the rock. And that's something we want to understand a little bit better. But it is definitely giving a very strong magnetic signature to the rocks. And this just shows you where these 4 sites are. So we've got 2 up here on the very, very top, and then 2 down here, well, 1 down here on this little edge, and then 1 kind of halfway up where there was a protruding rock ledge, not quite as prominent as this one, but where another layer was weathering, resistant to weathering. Okay, and in this study, the minimum and the maximums that we got out of these 4 different sites led to quite large, up to 19,000 nanoteslas difference between the low and the high in this very small area. There was less than 10 meters on each side, and compares reasonably well with what we saw at Vredefort, which is a different lithology. This was granite. So we went back and collected a lot of susceptibility data, because if we have the total field and we have the susceptibilities measured, we can then say that if we can't model it with the susceptibilities, it has to be remnant magnetization. We also did collect a sample for remnant studies, but in order to get a big enough sample to do something proper, it would be very, very difficult to map this out properly. So we took a very small sample that we could see was affecting the compass needle when we moved the compass over the rock. So we knew it had remnant magnetization in it. And Leonie Murray up at the Council for Geoscience has been working on that one. So one of the things we did was we looked at one of the freshly fractured surfaces, and we took susceptibility measurements every 10 centimeters down that surface. And we see some variation, but susceptibilities that are less than an order of magnitude difference are really not too meaningful in these basalts, because they do have quite a bit of variation anyways. It might be interesting to see if this is a flow top and deeper into one of the flows. That's something we could look at to distinguish some of the flow units. But certainly from this point of view, these susceptibilities are not changing dramatically. This is one of the larger susceptibilities we got, and this is the instrument we use. It's the handheld SM30 magnetic susceptibility meter. And it's incredibly portable and incredibly useful and easy to use. So it's very good in this kind of remote area. And so here's a compilation of about half of the susceptibilities we collected. This is 650 measurements. And we see that most of them are in quite a fairly narrow range, varying by maybe half, these are double these. So not, maybe one order of magnitude difference between these. So not huge differences, and certainly not enough to give you a 20,000 nanotesla anomaly. So if we can't do it with susceptibility, we must do it with induced or remnant magnetization. Okay, and here's a plot of the susceptibilities. Unfortunately, all the dots where we took measurements don't all show up, but this is about 600 dots here of the measurements we've got. And we can see some variation, but it's not very systematic, and it doesn't look that different from some other lava flows that are some basalts that we've looked at. Okay, so now to move on to the actual magnetometer data. I just love taking photographs up there. It's so beautiful. And this is one of the sites we looked at. This had, this is one of the, I don't see the rock where it is. I think it's right behind Jasper here with the magnetometer on him. But one of the rock we showed where we took susceptibilities down the face, you can see that this is a particular basalt unit. And so we collected magnetic data over this edge to try to see where there was an effect on the rock itself. And you can see our tape measure is out here. And of course, we have some spectators. And so we came back up here. Here's just to remind you again, here's our little peak. Here's our edge that we're interested in. And here's the a reminder of where all the sites are that Jasper and Stefan worked on. And then here's our magnetometer data. So we were able to get quite high up on the sides here, but then the slope becomes very, very steep. So we weren't able to collect data here. And we are only able to go up to the edge safely. So we didn't want to, it's a good 2-meter fall here. So we wanted to be safe. And you can see how on the very top, we're obviously getting a lot of lightning strikes on the very, very top, and then right on the edges here. And in fact, this little ledge here that pops out and is an outcrop also has quite a number of magnetic anomalies on it. And if we zoom in on that, we can see some of the features. And so these are all what we're proposing from the magnetic data as lightning strikes. And it's not clear that we can distinguish individual strikes. There may be several strikes contributing to the magnetic signature. It's not really going to be possible to say, this is one strike, this is one strike. But we're trying to develop a feel for how we can get a minimum and a maximum number. Certainly up here, we've got just a mess of lightning strike and lightning signatures. It really demonstrates how pulverized or how pounded these rocks have been by lightning. And we can see how quickly it tails off as we go up the slope. And in fact, just this little ledge here even has quite a number of strikes on it. And that's just without the overburden. Okay, and then the next step was to look at the regional data. And so the backdrop here is, this is kind of Google Earth attempting to do topography. This is obviously not very good because this is actually quite flat here, and this is quite flat on top. But we've overlaid the lightning strike data from the lightning network. Okay, and that's just to show you the magnetic data again. So now we're going to look at the lightning strike data. And this is what it looks like if you just plot it plain. Okay, so you just take the stats the way they come out, plot the locations, and contour it up and image it with colors. So the reds are higher strikes and the greens are lower strikes. And not a big surprise, it looks very much like the topography. And this is our study site. And if we zoom in on that, we can see our little peak here and that little nose that comes out. And then if we zoom in again, we can see the peak here has a little bit of a higher strike zone than the surrounding area, say down here. And so what Hugh has been working on is looking at, we have 11 years of the lightning stroke data and looking at the ridges and peaks and trying to get a probability plot of where the lightning strikes are. So to remind you again, this is our little tiny peak, and this is the edge that we're looking at. So we probably need to zoom in even more to get an idea. But with 11 years of data, we can start to make a guesstimate of how many lightning strikes per year we're getting and see if that correlates with the magnetic signatures that we see. So how long does a magnetic signature last before it's blasted off? This gives us an idea of some of the weathering rates. And that's kind of the exciting work we're looking at. And so just to summarize, the lightning is responsible, we believe, for large amounts of angular bedrock debris. There's no way that debris came from above because there's absolutely nothing higher in the area. The range of susceptibility values is too small to account for the magnetic anomalies. Therefore, the lightning-induced remnant magnetization must be responsible for these large amplitude magnetic anomalies. The magnetic data supports the hypothesis that lightning is important in the rock surface weathering and debris generation. And other studies have commented that climate change data suggests that the rate of lightning strikes will increase, and this process will become even more important and was possibly important or more important in the past. So also to point out, the strike network data are consistent with the magnetic data. We're getting numbers that are similar enough, you know, as we bracket our high and low estimates from the magnetic data and the lightning strike data, we can estimate that they're within range of each other. So I will leave it there and happy to take questions.
Well, thank you very much, Sue. That was absolutely wonderful. Yeah, that's a lot to that we just don't think of when we're measuring AMT, you know. So while we wait for questions to come in, I'll just ask a quick one, and that's referring to the density plot you showed correlated with topography. It looked like, yeah, the first order effect was there, but there were some peaks that where the strikes were not as dense as on other peaks at the same height.
And that's one of the things we're trying to understand in the data is because we don't have the actual original data, you know, we're not doing the location algorithm. Oh, I see. Yeah. So how does that affect? Yeah. We're given the confidence ellipse and not the actual data. So, you know, you're kind of, it's a very frustrating thing because, you know, we're used as geophysicists used to working with earthquakes and have the original data, and here we don't. So it's trying to work with these statistics. And I don't know how much of a network effect is involved in, the geometry of the network, how much that affects the location. Right. It certainly does in earthquakes, and it certainly must do in this.
Yeah. Yeah, we've got a comment from Louise Palome. Interesting results.
Louis Palome, yeah. Hi, Louis.
Some lesson there for the people doing high resolution, close to surface mag surveys for geoengineering applications, certainly.
Yes.
Thanks, Louis. And we have a question from Chong Lee. I'm going to read the questions out so it gets in the record.
That's great.
Excellent study supported by scientific data. Are you aware of the work of this company? Dynamicmeasurements.com. They use the lightning strike data for geological and geophysical applications.
What was the name of the company? Is that
Dynamicmeasurement.com.
Oh, I see it here now. Yeah. I'm not aware of their work directly, but I do know there are a couple of people doing things. Yeah, I'll have to look into that. Thank you. That's great.
Yeah, thank you, John.
Copy that.
And Yaro Gutierrez, sorry for mangling your name. Yaro, good afternoon. Do you think this type of study can also be applied to explain some appearance in carbon-bearing regions?
Not sure what you mean.
No.
I think what you're referring to is that it's more conductive or magnetic. I'm not sure that, that was the whole point about the lithology studies. There's at least 2 or 3 master's projects and a couple other projects that really show lithology makes almost no difference. And in fact, an honors project here, because we've got the magnetic shales are outcropping just up the hill. And we thought, gosh, that must, must attract the lightning and doesn't seem to have any effect that we can see within the resolution of the data.
Right, exactly, yeah.
Yeah. And so that becomes an issue. Are the locations good enough to really determine that? And I think that's where we have to start incorporating these ground studies where we can say, actually the rock has been hit here because we can see it in the magnetic data. Yeah. So the damage might be over there.
Would it be possible to put a one of those lightning cameras on the peak and have it? I know it's a bit expensive.
Have it get hit by lightning.
Yeah, well, and have it triggered by lightning, and so you'd actually see a hit.
Well, I know. I mean, I think a lot of the work Karina's been doing is mainly with buildings. Certainly, she's got one of the cameras looking out over Johannesburg and just seeing these big towers get hit all the time. But I'm not sure how viable it is to, these are expensive cameras.
Yeah. I just think what you could put
he
on
might be able to comment on that. I think I saw he was here.
Yeah. I just think there's some sensors that you could put on that would somehow record how quickly the break is and whether it's exactly the same time as.
Yeah, and I think that's one of the things we've been talking about is what would be the most efficient way to do that, whether it's camera or seismometer or something else, because there are different ways to measure that triggering.
Yeah.
And yeah,
you want disposable equipment.
Yeah, well, and there's also a surprising number of people around. I mean, that's one of the reasons I showed that picture with observers. Every time you go up there, there's always
Okay, is there any more questions from the audience? If not, then I'd like to really thank Sue again. Absolutely enthralling talk, Sue, really brilliant. This EMinar is recorded and it will be on the EMinar webpage and also on the YouTube channel, the MTNet YouTube channel within a couple of hours. And Sue's going to send me
PowerPoint and the abstract.
And she might even send me an abstract. Who knows?
Yes. That's the plan.
Oh, Hugh Hunt is...
You send me that webpage that was posted in the Q&A and then disappeared.
Yeah, if you press unanswered, you'll see it, but I'll send you that.
Okay, thanks.
All right.
Is there another question?
Just a link to YouTube from Hugh Hunt. I don't know.
I think this might be another version of the talk I gave earlier. Maybe, I don't know.
Oakwood Lightning event from the Senchal Tower, November. Oh, I see.
Oh, okay. Right.
Yeah. Okay. Well, thanks, everybody. Thanks for listening. Thanks very much, Sue, for being here. And see everybody next week at the same time. Right. Bye now.
Thanks very much. Bye-bye.